So next speaker is Gerome Godillot from Arkema. He will give a lecture on high-performance polymer for next-generation batteries. Gerome has background in material science and electrochemistry. He earned his PhD from the University of Bordeaux in 2012. His doctoral research was focused on hybrid supercapacitor based on cobalt oxide materials, contributing to the advancement of high-energy storage technology. Following his PhD, Gerome worked 2 years at the R&D department of soft batteries on the development of advanced battery solution. In 2014, he joined Arkema and held several positions within this group, gaining experience in materials innovation and battery technologies. Today, Gerome is project management for gel polymer electrolytes, semi-solid state batteries, leading the development of next generation electrolyte solution for safer and high performance energy storage system. He is based at Arkema's LAC Research Center near Pau in France. His role in SOLVE project is to help partner to get the most Arkema's materials for the battery, for example, PVDF, ionic liquids, lithium salt, and I add from myself as carbon nanotubes. And he is also responsible on the scale up of solid electrolyte membrane production by dry process that will be used in 10 and 20 ampere hour solid state cells. So here I stop, and then Gerome, the floor is yours. Please go ahead.
Thank you very much, Henri, for this nice introduction. I hope you can see my screen. And yes. Good afternoon, everybody. So my talk today will have... My talk today will have 5 parts. First, I will give you some clues about Arkema, then talk about the polymers we are developing for gel polymer batteries or semi-solid batteries, then tackle some polymer development that we have on the ASSB, so the true solid-state batteries. And last part will be on the new solvent-free processes we are developing for the SOLVE project, and I will finish with some takeaways. So about Arkema, so you may know it, but Arkema is a world-leading company on about materials. We are making some materials. We are protecting them, and we are bonding them. And so this is basically our main business. We had a turnover of roughly 9 billion last year, and it's by thirds, so 1/3 about advanced materials, so mainly how to reinforce the strength and give more lighter materials. 1/3 of our business is dedicated to adhesive solution. We'll talk about that, and the other third is about the coating solution and primary materials. So we are a world company, so business is spread on all the continents with the aim of producing the materials on the same continent where they will be used by our customers. So 1/3 of our business is done in Europe, roughly 1/3 in North America, and the last one in Asia and rest of the world. So we are a company of roughly 20,000 employees, over 55 countries in the world with 154 production units. Regarding our role in the battery field now, so we are material supplier, and we do not aim at producing batteries. With 2 main fields, I would say, what we call inside and outside the cell. So outside the cell is everything that concerns the battery pack, or going from the cell to the module and then to the battery pack. So first, with materials regarding electrical insulation and mainly polyamide for the insulation of the bus bars. Also regarding thermal management, we provide some thermally conductive adhesive and gap filler for dissipation of energy. We also supply some polyamide, especially for the safety fire resistance. And I would say we have in our portfolio all these adhesives, sealing, and gasket for cell assembly and to going from cell to module and then to pack. We are now developing more and more materials for sustainable batteries. So we have our famous polyamide 11, which is bio-based and which is also used in the coating of bus bars. We provide hydrogen peroxide for the recycling of batteries. One of our latest innovation was the bonding and debonding adhesive. So it's adhesive that will bond during the life of the batteries, and with special treatments, they can be debonded at the end of the battery life for recycling. So it's quite interesting. And I will finish with some electrode binders that are being developed, especially for dry coating processes. So this was for outside the cell, for the battery pack. Now, if we look at what we call inside the cell, so also materials that go inside the cell actually, as a producer of polymers, we tackle mainly binder, I would say. This can be PVDF, so our very famous Kynar PVDF binder, and also waterborne acrylic. So this is our Incellion binders. So both of them can be used at the cathode and the anode, but also as a separator coating. And this is quite a big application for us. Also, we have some components for the electrolytes, some advanced lithium salt like LiFSI, LiTDI. And recently, we acquired a company named Proionic, which supplies some ionic liquids. So these are high advanced liquids that are non-flammable, so very good point for the safety of batteries. And I almost forgot graphite strength, so it's conductive additive. It's multi-wall carbon nanotubes that helps for the electrical conductivity at the cathode or at the anode. So this was the materials we are supplying for current battery technology. So with liquid electrolytes. Now it has been detailed in the previous talk. People are addressing all solid-state battery with the aim of improving safety and energy densities. We see that it's a very challenging technology. Mainly due to the electrolyte interface compatibility and the pressure management that is related to this. So I would say a few years ago, a new kind of electrolyte appeared, which is called gel polymer electrolyte or semi-solid electrolyte. It's actually behaves like a solid, and it doesn't leak, but it contains some amounts of liquid. So the aim is to take the advantage of both of liquid and solid, so the safety and the energy density of all solid state, but the good interface electrolyte interface of the liquid electrolyte technology. So regarding these topics of semi-solid and solid-state batteries, Arkema tried to provide solution for all these technologies. So regarding gel polymer, we will talk about what we call ex situ or in situ processes. So in ex situ, the polymer is produced outside the cell, and the in situ processes, it's polymerized, and we inject a solution with the monomer, and the polymer is polymerized inside the cell. Regarding all solid-state batteries, so it's PVDF and acrylics, and the goal here is to address all kind of sulfide, oxide, or halide-based solid electrolytes, and by adding some polymers, try to decrease the pressure for the battery to work. So let's start with polymers for gel polymer batteries. So here, really the goal of this technology is to develop some battery with less electrolytes, or at least the electrolyte trap into the polymer matrix so that it doesn't leak anymore, with the global goal to increase the safety and energy densities. That's why we are tackled either lithium metal anode or silicon-rich ones. So here our portfolio regarding gel polymer electrolytes. So in situ and ex situ, we have the polymer matrix first. So ex situ is our PVDF kynar, and for the in situ, it's a water-based acrylic insulation. So since this kind of we start from a monomer that will be polymerized inside the cell, and we need some initiator, either thermal initiator, so Luperox, it's a peroxide thermal initiator, or UV initiator, like some photoinitiator from certamers. And we have again this additives or components for the electrolytes, so the lithium salt and the ionic liquids from Proionic. So let's start with the ex situ process. So process is very well known. It's solvent cast. First step is the dissolution of the PVDF into a solvent. Then when we add some lithium salt and some plasticizer, and because the PVDF is not conductive by itself, we have to add some I would say liquids to boost the conductivity. Once we have the solution, we cast it on a release film, dry it, and obtain a self-standing film, as you can see on the picture on the right. Self-standing film with no exudation of the liquid part. It's 20 microns thick, and it can be manipulated very easily. So this is the process to make the membrane, which will act as separator in the solid-state battery or semi-solid-state batteries. You know that for liquid-based batteries, the final step of the production of the battery is the injection of the liquid electrolyte inside the battery. Here for solid-state is a bit more difficult, because we have also to put this kind of solid electrolyte inside the cathode and in the anode also for silicon anode. So that's why we developed for these two processes. First one is impregnation. So it's quite simple. First step is like producing a membrane. We dissolve PVDF, mix with plasticizer and lithium salt, and then we cast it on a porous electrode, so cathode or anode, dry it, and calendering to remove the porosity. So this worked quite well, I would say, for loading that are not too high, because we do see that for high loading it's more difficult to impregnate well the whole thickness of the electrode. So for that we developed another process that we call internally all-in-one. So here it's almost a one-step process, and we mix all the raw materials of the electrode, so active materials and conductive additive, and the raw materials of the gel polymer itself at once in a solvent. So we mix everything, we cast, and we calender. So this second process is more interesting, but it's also more challenging, because we have to really manage formulation, the process, to ensure that the final electrode will have a good percolation, electrical and ionic percolation. So let's look now at some results and performances. On your left, you have some conductivity measurement for different temperature on ionic liquid-based GPE. So it's dark blue curves compared to classical carbonate-based liquid electrolyte impregnated in a cell guard separator. So what you can see is we get a very high ionic conductivity with our gel polymer. It's even higher than the reference, the carbonate liquid reference for temperature above 0 degrees. But these are total conductivity measurement made by impedance. What does really matter in lithium-ion batteries is the conductivity of lithium, and to get this conductivity of lithium ions you need to determine the transfer number of lithium, and this is a contribution of lithium to the total connectivity. So it's a value between 0 and 1. So for a transfer number of 0, the lithium does not participate at all to the conductivity. And with a transference number of 1, you have all the conductivity coming from lithium. So it can be determined by electrochemical measurement, like Bruce Vincent Watanabe. It's quite known in the gel polymer, I would say, in the polymer electrolyte community. And what we can observe on this figure on the right is if we determine the conductivity of lithium ions, it's the total conductivity times the transfer number. We can see that if we compare GPE based on carbonate and GPE based on ionic liquids, for instance, EMIM FSI, we get finally the same range of lithium conductivity for carbonates and ionic liquids. I will add that also ionic liquids will bring more safety as they are not flammable, and also higher electrochemical window stability. So I mentioned earlier that the kind of membrane that we are able to produce, they have a good ionic liquid and more generally plasticizer retention. We try to assess this with some kind of exudation test. So what we do is perform some cycling in temperature between 25 and 80 degrees. We can do up to 100 cycles, and we measure conductivity and check that we do not have any plasticizer exudation. And it's the case. This is a example with EMIM FSI, I think, and you can see that we are quite stable over 50 cycles. We also are able to assemble some post shells. So here it's NMC 622 against lithium metal, so gel polymer electrolyte at 25 degrees C/20, and you can see that we are able to reach more than 70 cycles at this stage, which is quite interesting. Let's talk now about the in situ process. So, as I said earlier, the backbone is acrylic monomer from Sartomer, and we had also either photoinitiator or thermal initiator. We have also the ionic liquids to boost the ionic conductivity. So here's the challenge with this in situ gel polymer electrolyte is really to manage the transformation from the initial state where you have a liquid, because it's a mix of a liquid monomer, plasticizer, and lithium salt, to the final state, which will be a gel polymer. The main advantages of this kind of technology is productivity, because you don't have this kind of polymer dissolution that you have for ex-situ. So directly you have the precursor solution, you inject it in the final state of the production of the cell, and then you launch the curing or polymerization, and it's done. So it's quite fast. Also, a big advantage is since you inject a liquid solution, it makes this process compatible with conventional cell assembly. So it means that you can implement it quite easily in the current gigafactories, or at least battery plants with process close to one already existing, and also no solvent are used, because the liquid part is only the monomer. And so the challenge is really to master this polymerization reaction, so going from the liquid to the gel part, because it will have a very huge impact on the properties of the gel polymer electrolyte you will get at the end. Especially, it will affect the ionic conductivity, electrochemical stability windows, and also mechanical properties. So for that, we have developed different kind of characterization to really trigger the advancement of the polymerization reaction and to determine if the polymerization is over or it's still in progress. So different techniques have been implemented, and especially impedance, DSC, NMR, and Raman. And so just to show you an example, so key parameters here is parameters that will manage the polymerization itself. So temperature, curing duration, the monomer content, the content as well of the initiator. You can play also with the functionality of your acrylic monomers, and also some additives you can add. And when you can see on the two figures on the bottom is depending on the parameters you are using for this in situ polymerization, you indeed get different performances in terms of cycle life. The blue curve is way better than the two other, and also red capability as a function of the C rate. So it's key parameter to manage to really ensure that you at the end of the process you reach a truly gel polymer and not liquid electrolyte. So let's talk now about polymers for SSB. So here we develop materials that are compatible with new components used in the all-solid-state batteries in order to increase safety and energy densities. And as I said earlier, we are trying to develop some materials to help ceramics, so oxides, sulfides, halides to manage pressure and allow them to work at a lower pressure. So the key point here is really first to handle the compatibility of the polymers that we are developing with the ceramics themselves, because except oxides that are very chemically stable, sulfides and halides are very highly sensitive materials, and they are sensitive to moisture, solvent polarity, and in case of reaction, you have some big security and risk related to their degradation with the formation of H2S with sulfides and so on. So already, I would say the first step in the development is to look at the compatibility of our polymers with the conductive ceramics. We have to first ensure that they are not degraded by the ceramics, and they will not degrade the ceramics themselves. Second step is to find when you are working with a solvent. The second step is to find a suitable solvent. So this is mainly aprotic and apolar system when you are talking about sulfides and or halides. And so here I give you some examples in sulfide systems. So sulfide PVDF hybrid. If you look at the curve on your left, you see conductivity measurement as a function of the percentage of PVDF in the hybrid. So it's a special grade of PVDF developed for this kind of application. Regarding all what I said before, compatibility and flexibility. So if you measure conductivity as a function of the amount of PVDF, for sure, the conductivity will decrease as much as the hybrid content is increasing. So it's kind of expecting of a dilution effect. What is more interesting if you are looking at the cycling. So the top one is symmetric lithium-indium solid electrolyte lithium-indium cells. So it's lithium stripping plating, and you can see that with 7% of PVDF, you improve, I would say, the symmetric cycling by decreasing the overpotential, and especially at very high intensity. Surfacic intensity. We also developed some full cell, and where we were able to demonstrate some cycling. So some tens of cycles were obtained with an excellent coulombic efficiency. So really here, the goal is to really define the compromise on the amount of polymer. The more you add, the more flexibility you will be able to bring, but the less conductivity you will have. So it's like I would say always, it's always a matter of compromises. And now we can tackle the last part, which are the new solvent free processes. The new solvent-free processes. So this is a topic that we are developing in Solve. So, like I said earlier, most of the gel polymer are produced by solvent cast. So the PVDF is solubilized and mixed with the other component. It's coated, dried, and calendared. And then if we are talking about an NP like solvent, you have to recycle the solvent after drying, purify it, and reuse it. So it's a lot of time and energy consumption. So that's why we are looking at also dry or solvent-free processes like extrusion. So in one step, you are able to mix everything and get one film that you can calendar in a second step. So no solvent, no drying, and it can help you to major saving in terms of economic for sure, but also CO2 emission and manufacturing footprint. So what we are doing is so it has been also presented a little bit in the previous talk. So extrusion will able to, so in the extrusion process, and we will first melt the PVDF and mix it with plasticizer and lithium salt. We are able to extrude a rod that you can see on the center picture. Or with a flat die, we can extrude also a film that we will calendar in the second step. So for now, we are able to obtain film as thin as 100 micrometer. It has to be improved yet and to reach a target which is something like in between 20 and 50 micron. But it's quite I would say good proof of concept. Also, the electrochemical performances are I would say decent for now, so it's very interesting. Our major next step will be develop continuous mode, because right now it's more like a batch mode. This means that we produce a film in one step and then take the film and calendaring right after. So the goal is to make it something like really a continuous mode with a winding of the calendar film, and at the end to be able to produce big quantities and supply our partner for the assembly of the 1 to 20 ampere post shells that have been targeted through the project. And I think now we are getting close to the end with the conclusion. So I hope I have been able to convince you that polymers will play a key role in the next generation of battery solution. We have shown some promising results and strong prospects for the polymers in gel electrolytes, whether in situ or ex situ processes. We have seen also that polymer binders for hybrid polymers, connective ceramic batteries will enable the deployment of this new battery design in mobility application due to the fact that they will help us to work at lower pressure. And finally, we have shown some polymer materials enabling the manufacture of gel electrolytes using dry processes, which is a major level for sustainability. So I would like to thank, to finish, the European Union for funding the SOLVE project, and thank you for your kind attention.
Thank you, Jerome, for a very interesting and I would say practical lecture. So you show a lot of materials that is important also, that and we see that your company covers different methods, different type of materials, different approaches, and I think it's always good to know about this. And so I think we got two questions regarding your talk, and from one person, Vishnu. And the first question is, what are the main difference in the physical properties of gel electrolyte and solid polymer electrolytes? Also, can gel electrolyte be used in roll-to-roll processing?
So the difference between gel electrolyte and solid. So solid electrolytes, or now we even call it a true solid electrolytes, to really make the difference in between. Solid electrolytes or true solid electrolytes do not contain any liquid, so any flammable component, I would say. In comparison, gel polymer electrolytes, it's based on polymer with some plasticizer. So some of them, I would say, the majority, it's carbonate, so it's very flammable. But if you are using any liquids, it's better because there are no vapor pressures, so they are very much preferred regarding the safety. And the second part of the question was.
Can gel electrolytes be used in roll-to-roll processing?
Yeah, sure. Roll-to-roll, yes. We can process basically gel polymer electrolyte like we process cathodes. We can produce this kind of membrane on the same kind of equipment, coating line, where we are producing cathodes. So it's fully compatible with roll-to-roll process as well.
Yeah.
And we do it. So I did not mention what process, but at Arkema we have a semi-industrial coating line where we can do that.
Okay, thank you, Jerome. So also you have another bunch of questions regarding in situ polymerization. So could you please explain how in situ polymerization can be implemented in battery manufacturing, and would an additional separator still be required to prevent short circuits?
So, like I tried to show you, so I will start with the second part. I did not mention it, but for now, for safety reason, people prefer, and because again, we are material suppliers, so we try to develop materials and demonstrate their performance. So for that, we have to build our own batteries, but we will not be the battery producer. But what we understand for now is, for safety reason, people prefer having a separator having a separator in this kind of institute. And if you think about it, I said it would be like same process for liquid electrolyte. So if you think about the process, you will assemble a cathode and an anode. So if you want to avoid any short circuit during the fabrication, you need to have a separator. So yes, a separator that will impregnate with the precursor solution. And first part of the question was?
It was about 1 second.
So
how it can be implemented in battery manufacturing in situ polymers.
So yes, this is the main advantage, because you start with a liquid precursor solution that you can inject in the battery the same way you do for liquid electrolyte. So in principle, yes, it can be done.
Okay, clear. And also we've got another question from audience from Felix Scharf from Julius. So thank you for the interesting talk. In your opinion, what is the biggest challenge for your materials when used in power cells? Compared to liquid electrolytes, your power cells only last 70 cycles to a state of health of 80%. What is the biggest challenge for your materials when they are used in power cells?
So clearly, here I would say the holy grail of this all solid state battery and semi-solid state battery is that we will use a lithium anode that will bring way more energy densities. But what we do realize, either with gel polymer, but also for true solid state electrolyte, is even if we have this solid electrolyte, it doesn't break dendrite. So dendrite growth is the main challenge. So what I showed you is, I would say, the first stage of development. Now we are developing some new kind of so it's we use this kind of block of the gel polymer that we've developed, but we improve it to really tackle this dendrite growth issue. And also just because we have realized it's the same issue for everybody in this field, we are also developing a solution with silicon-rich anodes.
So then I think we can close Q&A session for your talk. Thank you very much, Gerome.